Hello everybody. So, welcome to this class where we will be talking about the example of ligands, and we all know what are ligands, how they are controlling the coordination to your metal ion centers, then their biological origin. So, once they are available from the biological world, we can consider them as the biological ligands. So, definitely their occurrence and availability we can discuss. So, what are the things we will be discussing in this particular class in terms of their concept, that how they are occurring, whether a simple amino acid can be available and whether that amino acid can function as a ligand for any particular type of metal ion, and what sort of amino acid is it, that means the donor groups available in it. Then the corresponding elemental composition, that means in terms of your oxygen, carbon, hydrogen and nitrogen for a basic amino acid, say like glycine. Then Metallacycle ring formation, when the metal ion is binding to that particular site, how the ligand part is can give you the corresponding cycle formation, including that metal ion, and the thermodynamic and kinetic aspects of the stabilization of the metal ion complexes. So, all these different life processes what we will be talking and what we are discussing, they are dependent on something which can be discussed and which can be considered in terms of a particular thermodynamic quantity or the equilibrium process, or equilibrium thermodynamic quantity is basically maintained by energy consuming chemical reactions. So, if you find some simple reaction from left to right, A plus B is reacting giving you C plus D, but that should be energy driven, otherwise it will not go from left to right. They are very highly reactive, A is reacting with B producing C and D, but you must have something, the affinity for that particular reaction, such that you can move from left side to the right side. From the energetic point of view and the rate point of view also, the input and output which are essential for thermodynamic quantities for a particular open system when we talk in terms of your energy flux. If we think that this particular energy flux is required for your typical supply of energy in terms of your number of ATP molecules also, we can find in that way. So, if we have a particular stationary equilibrium, we can have the input and output and is in equilibrium. So, the amount of input, that means amount of thing going from by reacting A plus B to giving you C plus D. Similarly, after some time when some amount of C plus D has been accumulated in the medium, in the cell environment or within the cell, can start reacting. The C plus D can also react together giving back your A plus B, then whole thing will be in the equilibrium, and that is why we maintain the corresponding metal ion concentrations also, not only any other important biological molecules like your glucose, like your amino acids, like your peptides and other things. It is the homeostasis of the metal ions, and we will be focusing in all these classes on the homeostasis of the metal ions. So, if we have a particular thing, that means the energy gradient if we have from the lower to the higher one, and if we consider two flow equilibrium, but in the closed system which is a thermodynamic equilibrium, we know everything we study in our regular thermodynamic classes or the physical chemistry classes, that they are time independent processes. But if you have a open system, we have the output which is alternative one also, the input and output thing, how they are correlated for that open system is also a time dependent process, is not independent. So, this particular thermodynamics consideration is very much different what mathematically we can access in terms of its corresponding thermodynamic equilibria, the redox equilibria and all this. So, and the proton transfer equilibria also, the pH of that particular medium also can be correlated little bit with the thermodynamic equilibria what we study for the laboratory consideration. So, the cellular considerations will be completely different. So, when you find that this particular energy flux we get, then the life basically requiring a continuous material exchange, that is why you can have from one particular part to the other, which is in principle includes all chemical elements. So, if we consider, if we just focus our attention what I told you for your first slide or second slide, that you have oxygen, you have carbon, you have nitrogen and you have hydrogen. So, the elemental composition wise, why we write that some CX, HYOZ, like this the formula of the molecular formula or the chemical formula of a particular compound. Then when they are going for a different environment such that it can react with something. So, how they are occurring, all these elements, so elemental compositions, basically the occurrence of these elements in organisms like in our body, how we are made up of different proteins, polypeptides, metallians, amino acids and all these. So, they are basically dependent on the external and the endogenous conditions. That means, not the internal or other conditions, is the external as well as the endogenous conditions which is within. So, these elements starting from your metallians can be available in the biological world. So, their bioavailability of different extent is not that when you take food and our intestine is absorbing all this food material, is that you can absorb one particular metallian to a particular extent, but not that the other, but it should be enriched there. So, first thing is that how much it is available, what sort of food you are consuming, and that particular consumption basically tells us that okay, I have taken this much amount of that particular food which is rich in protein, which is rich in carbohydrate or which is rich in fat. But the typical absorption process, the typical assimilation process can go for reserve amount of these materials. We can store iron, we can store sodium iodide at some point if possible. So, if they are stored and if they are accumulated from the food material, we can consider them they are as bioaccumulated. So, organisms, any animals, any mammal or any human being, therefore, can use some active mechanism which is energy consuming processes involving a low reduction of entropy. So, entropy is not rising, entropy is basically reducing in this particular process. So, the energy what is being supplied for a typical adult, that these 4 elements OCHN. So, the typical amount basically, because we should have the higher amount of oxygen in terms of your water molecule, in terms of your oxygen in the carboxy end of the amino acid, in terms of your CONH function of the polypeptide chain as well as in the protein chain. So, the amount of in total, the amount of oxygen should be very high. So, this particular one in terms of a human body having 70 kilogram of weight, then next comes the carbon. So, how you get these carbons? So, if your food material can supply carbohydrates, we all know the carbohydrate is made up of carbon, hydrogen and oxygen. So, from there you can take up some carbon. So, the biosynthetic route in our body also, if the amino acids are not available from the external sources, you have to synthesize all these amino acids in our body, and carbon, oxygen, nitrogen and hydrogen are the most fundamental quantities in all these amino acids to proteins. So, then you have the hydrogen lesser amount and finally, the nitrogen which is the least amount. So, these 4 are the basically constituents for all these sources, what I just telling you, that is the source for your carbohydrate, is source for your protein and is also the source for your fat molecules. Then once you have these nitrogen bearing molecules, you have the corresponding acids thing is not your acetic acid, but is amino acids. So, you have to bring the NH2 function to it. Then you have the amino acids. So, amino acids giving you the peptides, then polypeptides and then finally, proteins in one particular structure. So, the whole protein molecule, if you have a big protein molecule, not that all these donor groups which are available, not only the CONH backbone, but also the pendant or the dangling groups or the dangling functions which are available can be useful for the coordination to the metallians. But sometimes we see that this protein can function as a test tube or a round bottom flux what you use for your laboratory reactions. So, this gives you an environment. So, it will be similar to a particular environment when you dissolve some metallian complex or metallian salt in some solvent like DMF, which is nothing but your NN dimethyl formamide. So, is amide is there. So, remember it nicely how we can correlate it. So, definitely it will have a basic CONH function, but that can function as a solvent. So, whether your polypeptide environment or the protein environment can function little bit about that sort of solvent environment. Then not only dimethyl, the monomethyl also, N-methyl formamide also can function with this particular way. And the way protein gives us this medium, the environment, the biological environment, this solvent medium can also give that sort of environment. So, if you consider something that you can have a biomimetic solvent environment, so you can think of having this dimethyl or monomethyl formamide to be taken as your corresponding substitute for the protein environment, such that you can monitor the ion-ion interactions as well as the protein-protein interactions in these particular complex environments. So, you bring now the metal ions, and the metal ion centers are quite often coordinatively unsaturated, that if you bring some iron ion into our system, is not that when it is not available for coordinating to your protein part or globin chain, it is fully coordinated by 6 water molecules, giving you a octahedral environment around say ferric ion Fe3 plus. Sometimes it is not there, it is not getting water molecules, but it is so pushed to some particular wall or somewhere, thus that you do not get that particular space for water coordination. So, with respect to the ligation, the amino acid side chains, so they are unsaturated with regard to the ligation. So, amino acid ligations are not taking place, and if they are not occupied by all other water molecules. So, these ligands then can use one non-adjacent donor atom for binding to a metal ion center as referred to as a chelating ligand. So, if you take a simple glycine molecule is NH2CH2COOH. So, what are its donor groups? So, its donor groups are nothing but you have the oxygen and you have the nitrogen. So, that basically gives us some very good idea that okay, if we have one donor groups like your ammonia, which is NH2 function of glycine, and another is your oxygen like water as a carboxy end. So, if we are able to bring both of them together around the same metal ion center, is very important thing, so that it can have the bite. So, the ligand can bite the metal ion, and the metal ion is here. So, that biting mechanism can give a corresponding ligand. Simple glycine, you write the glycine, know the formula, write it down, that is why we are not writing over here. You exercise yourself from your mind, you know the glycine, I am telling you the formula, then put it as the one nitrogen and one oxygen. So, it will be a bidentate enodonal ligand, your metal ion is there and it is forming two bonds, the metal ion oxygen bond and the metal ion nitrogen bond, and you get a whole Metallacycle. So, you have a chelating ligand. So, that chelating ligand is nothing but your glycine or the glycinate anion. And afterwards, when you have more complicated amino acid residues, not the simple glycine, you can have the histidine also. The imidazole residue is pendant or the hanging from the chain. That also can come and bind, giving a Metallacycle ring, and sometimes it restricts the torsional mobility of the system and contributes to the enhanced selectivity. So, these particular thing, due to the coordination, you are fixing something, you are stabilizing something. So, the torsion of the backbone CH2, sometime if you have the CH2 for the ethylene diamine say. So, how the torsion can take place. So, the torsional angle also will tell you how the backbone of the ethylene backbone of ethylene diamine or the bigger molecule like EDTA 4 minus, how the torsional thing can give rise to some torsional mobility of the system and contributes to the enhanced selectivity, such that in one conformation it will only bind one particular metal ion in a particular coordination geometry. Then the ring size of the chelating ligand, if you are ethylene diamine NH2CH2CH2NH2 with the metal ion forming a 5-membered ring, but if you have a propane diamine, you have a backbone of 3 carbon, 2 nitrogen. So, 3 plus 2 5 plus 1 metal ion is a 6-membered ring. So, these are the most stable thing, the 5-membered as well as the 6-membered one. Sometimes we find that you can have the 4-membered ring with the bigger donor groups like ethyl xanthate, you have bigger sulfur, here sulfur. and then is the RO. R is the methyl function or the ethyl function, RO, SS, and binding the metal ion. So, it is forming a 4-membered ring. So, C, S and another S and the metal ion. So, these 4 and 5 members, so all 3 together, the 4, 5 and 6 member rings are there. Some are small, the bite angle can be small, you need a bigger metal ion, and sometimes the bite angle is bigger, you need a smaller metal ion for the coordination. So, the chelating complexes then can exhibit enhanced thermodynamic as well as kinetic stability and the chelate effect. So, once you have the chelate which is binding the metal ion, and the driving force for that particular case, that how quickly we are getting, that means the corresponding equilibrium constant for your formation of the metal ion complex is important. Then one other factor, that how quickly they are forming, the stability factor in terms of its kinetics, the rate of the reaction. So, finally, the delta H naught or delta H 0 is the enthalpy gain. What we get out of these? So, you have the free energy change, the delta G 0, and for the optimum metal ion ligand donor interaction, that means the coordination. For the Metallacycle arrangement or the Metallacycle formation can be controlled also by the entropic factor, because if you have the corresponding aqua complex of Fe3 plus and you allow it to react with some bidentate ligand. So, when it is forming a triskelate, that means 3 bidentate anionic ligands or neutral ligands or a monoanionic ligand binding to your metal ion center, forming a whole entity where you have 1 metal ion center and 3 ligands. So, it is a species of 4 components, 3 individual ligands and the metal ion. By doing so, you are removing 6 water molecules from the surroundings of the iron center. Fe3 plus already bound to 6 water molecules. So, those 6 water molecules will be removed in the medium. That means, large number of particles are removed in the medium. So, you will have the entropic gain. So, the entropy gain out of that basically favoring that particular complexation reaction. So, this particular also favors the chelate formation, and because of the removal of the water molecules or any other small donor groups like ammonia or any other species like chloride sometimes, the fluoride sometimes and iodide also. So, that basically enhancing your corresponding complex formation. So, the stabilization with respect to the kinetic form of the chelate complexes basically reflects that most unlikely complete dissociation of such species, which would require the simultaneous breaking of several metal ion ligand donor bonds. So, why this you can have the stability? So, if you have 6 ammonia molecules or 6 water molecules surrounding the ferric ion center, then you bring 6 nitrogen in terms of 3 ethylene diamine groups, or you bring 3 nitrogen as well as 3 oxygen in terms of your binding of glycinate anion to the same iron center or any other metal ion center, and finally, you bring the EDTA, the bigger hexadentate ligand having 2 nitrogen donor and 4 oxygen donors. So, all we are thinking or talking in terms of nitrogen in isolation like ammonia, or oxygen in isolation like water molecule, or the bidentate ethylene diamine, or the combination of nitrogen and oxygen giving you glycinate anion, or another bigger combination where you can have the 6 donor ions available from one single molecule, that is your EDTA 4 minus. So, that is why the kinetic stabilization, if we are able to monitor, if we are able to measure, will have some effect when the bigger protein chain will come and trap the metal ion. So, if the other things are same of same type, then the chelate effect increases the ligand denticity, whether you have a bidentate or a tridentate or a hexadentate ligand. So, the number of donor atoms available for coordinating the metal ion is changing. When it is EDTA, the 6 numbers, 2 nitrogen and 4 oxygen will come and bind to the metal ion center, and at the same time you try to see and try to find out how many metallacyclic rings are forming. When EDTA 4 minus is binding to your metal ion center, this you can consider as your assignment. You work it out, you know it from your school days you are studying, but now you should remember it because this particular information and knowledges are always important, that what the number of metallacyclic rings are forming out of that particular coordination. So, this additional stabilization when a chelate ring is forming is also can be given to us if we have certain things that okay, I have not the bidentate, I have not the tridentate, but I have a tetradentate ligand. So, the tetradentate amine based ligand what you can consider and what you can think of is your N4 ligand, N4 tetradentate linear amine. So, diamine is your ethylene diamine, triamine is your diethylene triamine. Then the tetraamine will be, you will have the 3 ethylene backbone, NH2, CH2, CH2NH, CH2, CH2NH and then CH2, CH2NH2. So, these are basically at 2 ends you have the NH2 function and 2 NH functions. These are secondary amine and the end amines are primary amine. So, name of this molecule would be triethylene tetramine. So, that can also bind to your metal ion and that can also give you many such metallacyclic ring formation as well as the stability and the corresponding stabilization we can compare. But if we are able to connect, these 2 end NH2 functions, the primary NH2 functions, you will be getting a macrocyclic ring. So, it is basically a garland what we are putting on the metal ion. So, that particular things we can consider as the macrocyclic ring or the macrocyclic arrangement, such as we all know for our hemoglobin and myoglobin it is the tetrapyrrole unit, the porphyrin ring. The porphyrin is nothing but your macrocyclic ring. And if we can have a 3-dimensional arrangement, that means your crown ethers, ionophores are there which can bind nicely your sodium ion as well as the potassium ion. And sometimes if you have the one cyclic ring and then another ring from the one nitrogen end or one other end through the other end, you get a cryptand, because you have the basic idea. What is the basic idea? Basic idea is that you have to provide 3 plus 3 6 donor groups. So, 3 plus 3, but your macrocycles, the N4 macrocyclic like your tetrapyrrole giving my fingertips basically 1 2 3 4. So, these are your 4 nitrogen which is a tetradentate macrocyclic ligand. But if you bring like this arrangement, so this is connected and this is also connected. So, you will get a cryptad. So, this basically the cryptads, the cryptad type of ligand basically can enclose the metal ion within this particular pocket. So, it is a very useful, very good dumbbell shaped pocket, and basically this basically enclose and the stability will be much higher even if you consider only the binding of sodium ion as well as the potassium ion. So, those arrangements are basically very important and you should know about all these ligands. You go back your study table and open up the books what you have studied so far, all the different sorts of ligands. Otherwise, you will not enjoy these classes in terms of your metal ion and the ligand coordinations, because the many biological and the complicated things will come. But before that, the very basic ligand part we should have some very good idea on that particular point. So, since the chelate is forming, definitely we will have the chelate effect which have higher stability and the energy gain also in terms of that particular coordination. And you have the 3-dimensional structure, and if your protein is coming and the protein can give you the supply all these 3 plus 3 coordination sites like your cryptad. So, you have this, so you have the planar ring and then the planar ring is basically the, if you have a ring and then you have the corresponding connectivity like a handle and a basket handle. So, these basically able to determine something, that what are the ligands which are available for the coordination to your metal ion, whether you have only oxygen centric donor atoms available for your typical ionophores which are required for coordination of your sodium and potassium ion, or the typical nitrogen for binding your iron in your hemoglobin and myoglobin molecule in your blood. Their stereochemistry, that means the corresponding geometry, the corresponding geometrical isomers what are forming, whether you are getting a cis isomer or a trans isomer or a facial isomer or a meridional isomer, and sometimes the optical activity also, and the local hydrophobicity and the hydrophilicity. What is that? That means how much your corresponding benzene rings, or the hydrophobic organic part is there, or the hydrophilic anionic donor groups like the carboxyl attend, or some other amine end which is forming a ammonium ion or any deuterionic form. So, that can balance also, because everywhere the environment is your aqueous environment. Then finally, the secondary sphere of attractions, which in terms of your hydrogen bonding. So, that hydrogen bonding by nearby residues can also tell us that whether you can have some non-binding residues, and the metal ion can give you or fulfill or stabilize that particular metal ion coordination. So, now that particular chelation, how we can apply to not only your biological inorganic chemistry, the biological inorganic chemistry with special emphasis to metal ions, what the biological world or what the biological information can give us in terms of your corresponding coordination chemistry. It can also be applied to your medicinal chemistry. So, it can be considered as the medicinal metal ion chemistry or medicinal inorganic chemistry also. So, this chelation is very much important. We have the corresponding metal ion in our body if we want to supply the typical metal ion, but that will not be very much or very nicely assimilated in our body. Like your platinum, we know that the platinum you can supply as a anti-cancer drug in the form of your cisplatin, but we are not injecting the patient with that of your platinum salt, the platinum chloride, or your tetrachloroplatinate, or your H2PtCl6, many number of these platinum salts are available, but a particular type of coordination complex, which is your cisplatin, is given for your corresponding treatment. So, one such example now I take here is your that particular thing, which is a very huge and a long molecule, but is not of your type what we are discussing. We will be discussing about your polypeptide chain, but is a very long molecule, and what we can synthesize in our laboratory also, and what we will be looking for when you get a long chain like your triethylene tetramine. It has many other things, many other applications, starting from your organic chemistry to the polymer chemistry. Those triethylene tetramine molecules are very useful for all these purposes. Similarly, one such long chain organic molecule is available to us, and if we look at the adjacent bidentate part, the NOHCO is NOHCO part. So, this particular NOHCO part, then another NOHCO part, and then at the end basically CH3CO NOH part. So, it is basically the hydroxamate function what we are looking for, and that hydroxamate function is very much useful if you are facing the toxic effect of your iron centers. That means, you have many number of iron. By doing some medical treatment on all these things, you have accumulated huge amount of iron, and that is getting stored in your liver. So, at what time, what will happen? The storing of these iron there, like your iron nail or iron rod or iron knife or anything, getting rusted. So, immediate accumulation of these iron over your liver is basically, or your pancreas or any other vital organ, if it is deposited over there, you will all be rusted, your liver will be rusted then. So, a particular type of disease, a hereditary disease you cannot avoid, is a genetically transmitted disease, is your thalassemia. And this particular thalassemia, occasionally we require the new blood supply, the blood transfusion. So, more and more blood is given to your system, but your system is not accustomed to remove the other metal ions. We extract some amount of metal ions we remove from our body, but when you are consuming some extra amount of iron in terms of your blood, and the blood after some time is getting degraded, it has some lifetime of around 120 days. So, 120 days, after 120 days this blood will not be useful, you have to synthesize your new blood. So, to remove that particular one, this particular chelator, which is desferrioxamine, which is known as desferral, is DFO, is a commercial trade name having this thing. So, this is a very useful chelate which can bind that particular free iron ion and can remove all these iron or iron overload or the toxic effect of iron from your body. So, what we have seen in this particular class and what we have try to understand in this particular class by showing these examples of these starting from your ligand, your metal ion, how it is binding, and finally the corresponding application. One such application always you should know about the application of this particular drug molecule is a typical drug molecule to remove your iron from your body when you are undergoing some treatment. So, the application of this experimental coordination chemistry, what we are doing in your laboratory, is not that theoretically we are talking about the ligand and the metal ion and okay, it can bind or it may not bind. But the experimental thing is always important, which can support the clinical understanding the doctors are doing, the pathologists are doing, or they are serving all these purposes. Because we the chemists also read, teach and learn the biochemistry. Similarly, the doctors, the practicing doctors also, they also study the biochemistry, but their understanding is towards the clinical chemistry. So, this particular part, that means the coordination chemistry, what we can understand from these in terms of the metal ions and the metal ions which are available in the biological world, like the availability of the iron from our food material for the synthesis of new hemoglobin and myoglobin molecules. Okay. So, book will be covering for this is that the typical, you just go for Wikipedia page for searching only the bioinorganic chemistry. Okay. You can get all these informations, and the book we can follow is the biological inorganic chemistry, is the latest edition, is the 3rd edition, remember it, because it has also the other editions in 2012 and 2007. So, because all the latest informations what we are trying to cover, because it is not that a typical or the other bioinorganic chemistry what we know. So, the latest informations what we can gather out of these is for the latest book what you can have. So, thank you all for your kind attention.